Calculation of the mean free time tau. The probability P of t dt that a molecule having survived without a collision for a time t suffers a collision in the time between t and t plus dt is P of t omega dt. So it didn't suffer a collision, now it suffers a collision in the time interval dt. Part A showed that this probability is properly normalized in the sense that integral 0 to infinity P of t dt is 1, and this merely asserts that the probability is unity that the molecule suffers a collision at some time t. Okay, so the probability, this funny P of t dt, that a molecule having survived without a collision for a time t suffers a collision in the time between t plus dt was P of t omega dt. So normalization of this integral from 0 to time 0 to infinity, we have this P of t dt is integral from 0 to infinity, because that probability of having survived without a collision for a time t, suffering a collision in the time between t and t plus dt, is P of t, the probability of survival for time t, times the probability of having a collision in the time interval dt, omega dt. So this we have found to be integral 0 to infinity P of t. In the previous problem we have found to be e to the minus omega t. So we have e to the minus omega t omega dt. Now let's have omega t equals x, so that dx is omega dt. So when t is equal to 0, x is equal to 0. When t is equal to infinity, x is equal to infinity. E to the minus x omega dt is dx, and this integral is minus e to the minus x evaluated between the limits x equals 0 and x equals infinity. This is minus, at infinity it is 0, at 0 it is 1. So this gives us 1 as expected. So we have shown that this probability is normalized, implying that the probability is unity, the molecule suffers a collision at some time t. Part B, use the probability funny P of t dt to show that the mean time tau during which a molecule survives before suffering a collision is given by 1 over omega. Okay, the mean time tau, which is t bar, is the integral from 0 t equals 0 to infinity t P of t dt. This is the integral from 0 to infinity. This was funny p, now this is the real p. Probability of survival up until time t, probability of a collision in the time interval dt. So this is probability of having survived for a time t, having a collision in the time interval t to t plus dt. So we're taking the average value of the time of the survival before the collision occurs. So we have average value of t, funny P of t dt. So this gives us the integral from 0 to infinity omega t e to the minus omega t dt. And let's do the same transformation. Let's have x equals omega t, dx equals omega dt, and t is x divided by omega. So with that, we have this integral becoming at t is equal to 0, x is 0, t is equal to infinity, x is infinity. For t, I substitute x over omega. For omega dt, I substitute dx, and for e to the minus omega t, I substitute e to the minus x. So at this point, I will do integration by parts. So let's call ux dv e to the minus x dx, so that du is dx and v is minus e to the minus x. And this tells us that tau, mean value of the time t, is 1 over omega uv minus integral v du. Integration by parts, that's what I'm doing here. Integration by parts. And this becomes 1 over omega uv, which is minus x e to the minus x, minus integral v du. Well, v has a minus sign in it, so this becomes plus integral 0 to infinity v du, which is dx. And this is to be evaluated between 0 and infinity. So this gives me 1 over omega. Now, if I evaluate this at infinity, I will get e to the minus infinity, which will give me a 0. If I evaluate at 0, I will have 0. So this is 0 plus 0 minus e to the minus x evaluated between 0 and infinity. And that gives me tau is equal to 1 over omega. I will have evaluated infinity is 0, evaluated 0 is 1, so it is minus 0 minus minus plus 1. So this gives me the tau, mean free time, to be 1 over omega. Okay. Part C, express the mean square time in terms of tau. Now, mean square time, t square bar, is integral from 0 to infinity t square p of t omega dt. And now I have omega t is equal to x, t is equal to x over omega, and omega dt equals dx. So with that transformation, I will have for t square bar, t square is x square over omega square, so this is 1 over omega square, integral from 0 to infinity x square e to the minus x omega dt is dx. So we will use integration by parts again. U is equal to x square, du is equal to 2x dx, dv is equal to e to the minus x dx, and v is equal to minus e to the minus x. That's the integral. So this gives us for t square bar 1 over omega square uv, which is minus x square e to the minus x evaluated between 0 and infinity, minus becomes plus v du, which is 2 integral 0 to infinity x e to the minus x dx. And this part gives me 0 again. So I will be left with 2 over omega square integral from 0 to infinity x e to the minus x dx. Now integral 0 to infinity x e to the minus x dx gives me 1, so that this answer is 1 over omega. So this basically was shown to be equal to 1. This is shown in part B. Therefore, I can see that t square bar is equal to 2 over omega square, which is 2 times tau square. All right. So The probability, this funny p of t dt, that a molecule having survived without a collision for a time t, that's this p of t, suffers a collision in the time between t and t plus dt, that's omega dt. So these two events occur jointly. Then we have p of t omega dt is funny p of t dt. That is the probability that it suffers a collision in the time between t plus dt and not suffer the collision for a time t. Now, this probability of suffering a collision in some time integrated between 0 and infinity is the probability p of t, which was shown to be e to the minus omega t in the previous problem, omega dt, integrated when we set x equals omega dt, dx equals omega dt, dt. This gives us e to the minus x dx, whose integral is minus e to the minus x. If you differentiate, you get the minus signs cancelling and you get e to the minus x. So at infinity, this is 0. At 0, it is 1. Minus minus 1 gives us 1. So this is properly normalized. So there will be a collision at some point. Now, we use this probability distribution to find tau is equal to 1 over omega. A molecule survives before suffering a collision. The mean free time a molecule survives before suffering a collision. The mean value of time t, the time before it suffers a collision. When does it suffer a collision? In the time interval t to t plus dt. Okay, so that is the integral 0 to infinity t e to the minus omega t dt. Omega dt. So here I have, for this, that's what I'm substituting, p of t omega dt and multiplied by t, integrated over all possible time values. Here I use integration by parts, use x du is equal to dx, dv is e to the minus x dx, v is minus e to the minus x. With that, using duv equals udv plus vdu, we can see that uv minus integral vdu is integral udv. That's integration by parts. So applying this here, we obtain tau is equal to 1 over omega. So we have uv x e to the minus x with a minus sign, minus minus plus integral v du e to the minus x dx, and that gives us tau is equal to 1 over omega. And by the way, we see that this integral 0 to infinity x e to the minus x dx is 1, so that the answer is 1 over omega. In part C, we want to know the mean square time in terms of tau. The mean square time in terms of tau, that is, we replace t in this integral with t squared and apply integration by parts twice. The second time we apply it, we encounter the same integral we have encountered in part B, which was 1. So we find our final answer, 2 over omega squared, which is 2 times tau squared, because tau was shown to be 1 over omega.